looking at section 10.6, nonlinear regressions. Okay, so when we start talking about nonlinear regressions now we're going to step away from our straight lines, and we're going to have all sorts of curves. Sometimes it can be easily found, sometimes they aren't as easily noticed. So what we're going to do is we're going to test to the 5 main ones that were given to us. We're going to test towards logarithmic, power, quadratic, exponential, and then linear is always a good one that we'll toss in there just in case, because there's sometimes we might think that they're nonlinear, but linear is a best indicator on there too. So looking at problem number 6. Okay. On problem number 6, they give us this table of x and cost. Okay, so we're going to come into a spreadsheet, so a list and spreadsheet, and we're going to title one x, and then the other one is going to be our cost. If you notice in the table, they give us 1, 1.5, 2, 2.5, and then 3. Going over then to the cost side of it, they tell us it's 35, 118.13, 280, 546.88, and 945. So one of the things we can always do is we can always look at this visually. So if we go to our data and stats part here, remember we can always pull up a scatter plot on here. X is our input, cost was our output. So we can look at this and we could say, well, hey, could be quadratic, but it only shows the right-hand side. Could be exponential, maybe a little better than quadratic just because it's showing that curve, but are we truly have a multiplication factor here or not? Could be some sort of power model on here. Logarithmic, probably not the case. Linear, probably not the case. We're not following a straight line. We're seeing a distinct curve. But once again, we'll test all of these so we can show you how we're going to go about it. So I would tell you on your table, anytime we go through this, we're going to go linear, quadratic, exponential, power, logarithmic. Now they can be done in any order. This is just the order that I happen to remember them, as I was just listing off right here. And then what we're going to find is we want to look for an r squared value. Okay, so unlike the multiple regression from the previous section where it uses the adjusted r squared value, here we just use the r squared value. So we can do this in multiple different ways. Okay. We can stay within our spreadsheet and run our test, but then we're going to get very confusing in there. My suggestion would be, once again, is to go to that calculator. And then in this calculator, we're going to run our tests through like we normally would. So if we come through with menu, statistics, now we're not actually doing a stat test, we're doing stat calculations, because we're just calculating out regression lines and accuracies on here. So if we come to our stat calculations, notice we have multiple different regression lines. So we can start with our linear regression line. I can choose mx plus b. Our input is x. Our output is that cost. And we come through and we look at this and notice we see an r squared value of 0.929. We're going to do the same thing. We're going to go menu, statistics, stat calculations, and now we want a quadratic regression. Once again, x, cost is our outcome on here. Notice it tells us quadratic right here, gives us our equation right there. R squared value here is 0.9994, so 0.999. Now we're going to go to exponential. Come down here, here's my exponential. We're looking at x for our input. Cost is our output once again. Here we see our r squared value is 0.974. Menu, statistics, stat calculations. Now we're on to our power regression. X is the input, cost is our output. Here we're seeing r squared 1.0, so it's not even giving us any, it's just saying 1. Okay, and then we kind of ruled out logarithmic just on how that curve was, but we can always toss it in there once again. We want you to list everything off so that way you can physically see what's going on. So we have that logarithmic regression. X as our input, cost. Now I will tell you, if you haven't noticed, a lot of these stat things pop up in here. Instead of labeling X, you can always label A for that first input, and then it always shows up at the top. That would save a little bit of time. So if we come to logarithmic now, we see our r-squared value is 0.828. Okay, so as we look through here, we see, hey, quadratic, 0.999. That's pretty much what this one is. But if we think about quadratics generally have a curve going like this. Our data was showing some sort of curve like this. That's part of this, but not the overall quadratic curve. Exponential is leading a little more closer to this graph, but that power model also does this. Okay, so in this case, we look at that power model. So if we come back and we arrow back up and we find where our power regression is. Okay, so our power regression model. Okay, so it's this one right here. It tells us that we have an equation that would be y equals ax to the b power. And then it says, well, y equals, so let's formalize our y hat equals, we would have then a, which is 35.0005, so 35, and then x to the b power, which is 2.999999, so 3. So we see that this is probably the most simplified equation on here. Would be a section of a cubic function on this. Once again, 35x cubed then would be our equation that follows. So this is how we look at nonlinear regressions. Depends upon the information given, what we have. We basically plug it in and we're just going to run these different regression lines. But unlike before, we're going to look for that r squared value. So you got to write that r squared value down for each of these 5 regression tests, these nonlinear regression, well, 1 linear, 4 nonlinear regression tests, and then we're going to pick out the most accurate. And if some are really close to each other, that's when we got to use a little more common sense in here, because this power model, a cubic, would have our curve kind of going like this, versus an up and or down and then back up. Once again, it depends. There will be some leniency on grading in here, but always try to choose the best one that would also explain the situation too. So if we know, like, populations are generally exponential working in there. So if we have a quadratic and exponential that are very close to each other, we would want to use the exponential model. Even if it was a little less accurate, it would be more correct in the overall process.